Okay. So guess what we're talking about today? Salts that are insoluble. And you guys had some practice at doing this, but basically we're talking about a salt AB where it's cation and anion, okay? And we're saying that it's insoluble, but to a certain extent it does break apart to form A+. I'll put AQ since we usually talk about we're dissolving it in water. Water is our solvent, to B- AQ. Okay, to just a little bit. And then we said that you can write a KSP expression. Okay, it's the molar concentration of the cation raised to its stoichiometric coefficient. In this case, I kind of said it's 1, stoichiometric coefficient of 1, but it wouldn't have to be, times the molar concentration of the anion raised to its stoichiometric coefficient. So we did some problems where you can you can calculate the KSP if you're given the molar solubility, or actually you can also get to the molar solubility if you're given the KSP. But in this case, basically you're going to try to dissolve this into something that's not pure water. So in this case, you're going to try to dissolve it, and successfully, to a certain extent, dissolve it in something, for instance, that already has A in it, or already has B- in it. That's the common ion effect. Common because basically you have a salt up here you're trying to dissolve, AB solid, and there's already some of that cation or anion in the liquid. Okay, so it's not pure water. That's it. That's the common ion effect. Well, that's one variation of it. So I guess this is this is what it is. So I spent a little bit of time looking at this at my office. I'm like, what? So here's a clear solution of lead 2 iodide. Actually, it's saturated. And one of the things you know about saturated solution is they're right on the tipping point. It can't hold any more lead 2 or I-, okay? It's saturated. And so here in this dropper bottle is concentrated potassium iodide. So here's the deal. When you drip potassium iodide in there, the thing you care about is the I-. So you're adding I- to this. Potassium, it's just a spectator. But the common ion is the I-. Okay? So notice we have a precipitate. Why? Because we added more I- in there. Okay? And that's stressing the solution. Le Chatelier's principle says one of the things you can do is add more product. And that's what we're adding. What did that do? It made it go to form reactants. What's reactants? It's the solid. So in today's problems, I'm going to really encourage you to keep doing this whole identifying the equilibrium of interest. So that's lead 2 iodide. So it looked like this, PbI2 solid in equilibrium with Pb plus 2 plus 2 I-. Does that make sense? Okay, that's the equilibrium of interest. So basically, we added more of this. Okay, this was in your dropper bottle in the form of potassium iodide. We don't care about the potassium at the spectator, but we do care that you added more of this. What did it make it do? Precipitate out. So that sludge right there, that is your PbI2 solid. That's how this works. Okay. All right. So let's work a problem that is what we call the common ion effect. So if you read this a few times, we're dealing with calcium carbonate, and we looked at calcium carbonate before, and we came up with the molar solubility in pure water of 5.3 times 10 negative fifth. Okay, so it looks like this. Okay, where this is pure water, and we know that we could go ahead and dump in 5.3 times 10 to the negative fifth. We could make this 5.3 times 10 negative fifth calcium carbonate. Okay, and it would all stay in solution. You'd be right at saturation. That's what molar solubility means. So now the common ion effect, it's saying, all right, instead of pure water, let's take it up a notch. And let's go ahead and in that, instead of pure water, we are going to make it 0.10 molar calcium nitrate. Can you see where actually the nitrate in that we don't care about? We do care about the calcium because that is actually the common ion in calcium carbonate. So one of the things this semester I'm going to kind of encourage you to do is, if this is the solution it's made up into, go ahead and show that calcium nitrate, go ahead and show it breaking apart into calcium plus 2 cations and NO3 2 minus nitrate anions. Then underneath there, what I'm going to do is go ahead and bring this information. So it was 0.10 molar in the calcium nitrate. So it's looking like we get, oops, I didn't balance that, did I? I need to put a 2 here.
Okay, that was...
Yeah, good catch, good catch. You're like, Mrs. Knives. Because that was going to be my point. So we get 0.10 molar of the calcium. How much of the nitrate do we get? Is it going to be 0.10 molar? 0.2. Yep, very good. Yep, that was my point. Okay. So here's the deal. I can't remember where I wanted to do, but I want to make an ice table here. And actually, I'm going to circle in orange. That is the common ion. It's in common with, and I'm going to go ahead and up here, I'm going to go ahead and write the equilibrium of interest. Okay, equilibrium of interest is that insoluble calcium carbonate. Calcium carbonate solid is in equilibrium with the calcium cation and the carbonate anion. That is your reaction of interest. This down here is just simply kind of showing you how you're getting your common ion in your, so it's not pure water. So does this make sense that if you already have, in this case, 0.10 molar calcium in here, that you're not going to be able to dissolve 5.3 times 10 to the negative 5th molar calcium carbonate? This molar solubility is going to be reduced because it already has some calcium in there. Okay. So, yep, I want you to get in the habit of anytime we talk about precipitate, go ahead and make it solid and show it ionized and showing it breaking apart, but it's in equilibrium. So the KSP for this is given. You get that from a table. So if you want to write table next to that, you can. I don't know if it was given a minute ago in this write-up, but that I would give that to you for this one. So I'm going to break out of my notes here in a minute and make the ice table that you see on the next slide. Okay. But these, getting to molar solubility now in a solution that's not water is similar to getting molar solubility of a solution, or molar solubility of something that is dissolving just in water. Okay. All right. So here we go. I told you, I know it's kind of strange, but I like to go from left to right. I like to write my calcium carbonate solid as being one of my columns. It's kind of dumb. And then I start with my calcium cation, my second column, and carbonate would be the third column. Initial, change, and equilibrium concentrations. So we said, like before, we said the initial concentration of your solid is basically an infinite amount. Like you saw on the previous slide, we're going to let X be equal to the molar solubility. So the change in my solid is minus X. Okay, the change in my cation is plus X because it's a 1-to-1, and the change in my anion is also plus X. But here's the deal. Can you see where this one right here, this box, this is what's different? The initial concentration of the calcium cation. It's not 0 anymore, isn't it? This is the common ion effect. It is 0.10. Does that make sense? All right. What's the initial concentration of the carbonate? Was there any in the water to begin with? Hopefully not, if it's pure. So that's still 0. So we get equilibrium concentrations of infinity for the solid, right? For the calcium now, we have 0.10 plus X at equilibrium. For the carbonate, we have X at equilibrium. And like we did before then, we can plug into your KSP expression, and we can say KSP is equal to the molar concentration of the calcium, which is 0.10 plus X, times the molar concentration of the carbonate, which is X. And of course, we gave that value of 2.8 times 10 to the minus 9th. Again, you get that from a table. So, here's the deal. What we talked about before is I can take this X and I can distribute it through that quantity, okay? And then I would get X squared plus 0.10X is equal to a number. I could rearrange it, get it in standard form and plug it into the quadratic. But I'm going to show you how you can actually take these to fruition by what we say apply a simplifying assumption. So here's the deal. The molar solubility, that X right there, this right here is very small. How do we know it's very small? Because we're talking about an insoluble salt. It should be very small. So if X is very small, and the simplifying assumption goes something like this, and you're going to need to use it for your homework and for the test, and actually for acids and bases that we're talking about in Unit 4. Okay? So it goes something like this. If X is very small relative to, in this case, the common ion amount, 0.10. If X is very much smaller, that's a double less than 0.10. And the reason I put 0.10 is because I'm trying to simplify that quantity. Then this quantity, 0.10 plus X, basically you can ignore the X, and so that quantity is equal to 0.10. That's called the simplifying assumption. And when we talk about acids and bases, we'll talk more about this simplifying assumption. But the cool thing is if X is appreciably smaller than 0.10, then this quantity, 0.10 plus X, becomes 0.10. And now let me rewrite your KSP expression. Now your KSP, after applying the simplifying assumption, is what? 0.10 times X is equal to 2.8 times 10 to the negative 9th. Life just got a lot easier. I can almost do that one in my head. To solve for X, we divide both sides by 0.10. Okay, that's the simplifying assumption. And here's what my notes say on it. Okay, this is the ice table. Now you can maybe see why I really like the ice tables, because it's easier than to step into it when we're applying, when we have a common ion in the water we're trying to dissolve it into. Okay. Initial change, and apply the change to the initial to get the equilibrium concentrations. All right. So, at equilibrium, the calcium ion is 0.10 plus X, where X is the molar solubility. At equilibrium, the carbonate is simply X, because there was no common ion of carbonate there. The third line is your KSP. KSP is equal to the molar concentration of each of them raised to the first power, which is, again, the 2.8 times 10 to the negative 9th. That's what you would look up in a table. So here's my simplifying assumption. If X is appreciably smaller, much less than, double less than signs, that 0.10, which is the common ion, okay, then the quantity for, in this case, the calcium, okay, that 0.10 plus X is approximately equal to 0.10, because you ignore the X. Okay, let's go ahead and solve it. Okay, so you'll get a value of X is equal to 2.8 times 10 to the 8th. 2.8 times 10 to the 8th. That would be the molar solubility, because that's by definition what X was in our ice table. The molar solubility of calcium carbonate if you already got calcium in there. What was the molar solubility of the other one? 5.6 times. 5.3. Oh, thank you. 5.3 times 10 to the negative 5th. Very good. So it's less soluble, which makes sense because there's already stuff in there. Okay. So you can check your simplifying assumption. Okay, so in this case, specifically, you can check your equality. We said X is significantly less than 0.10. Does this seem right? What did we get? 2.8 times 10 to the negative 8th. Is that significantly smaller than 0.10? I say yeah. There's your last homework, I want to say, that's going to be due for Friday. It gives you, it says, basically the simplifying assumption kind of fails, but I just go ahead and use the simplifying assumption and meet me on the other side. If the simplifying assumption fails, then you have to go back to the quadratic, which is doable, but everybody hates the quadratic. So let's take a look at these four that are going to be due on Friday. And just so you're not getting your hopes up, we are going to go forward into that last part of material, but we're not going to get to an assignment slide. Okay? So I'll throw you a bone. And I did push these hints out there. I don't know what's getting into me? Oops, that wasn't it. That looks familiar, doesn't it? All right. There will be one of these on your test, I promise. Right? Okay, so anyway. So we're dealing with magnesium hydroxide. And anytime they say calculate the molar solubility, already be thinking that must be an insoluble salt. So I went ahead, magnesium hydroxide, solid. I put it in equilibrium with its cation and anion, right? Make sure you balance it. I don't always balance mine, but make sure you balance yours. And then actually, I'll tell on myself, when I was doing this at my office, I actually, when I wrote the KSP expression, I forgot to square the hydroxide. But do you see why you have to square the hydroxide? Because it's a stoichiometric coefficient when that thing ionizes. Okay, so of course that KSP was given. So notice there's three scenarios. Basically, and I picture myself beakers, right? I picture myself three beakers, beaker A, which is water, beaker B, which has got a common ion, looks like magnesium's a common ion in B, and for C, it's got a common ion hydroxide. Okay? No, darn it. Come back. Pushed the wrong button. Okay. So there's my beaker of water. Okay, so you need to come up with the molar solubility in water, the molar solubility if you're putting it in magnesium chloride, And like I said, this semester I'm emphasizing what happens with that magnesium chloride, okay? What happens is basically the magnesium chloride is soluble, otherwise it wouldn't be an aqueous solution of that, ready to receive your insoluble salt. And it ionizes, and notice you get twice as much chloride ion as you do magnesium, but that's okay. So actually our initial concentration of magnesium is going to be 0.0862 on our ice table. And then last but not least is this scenario where again you're trying to dissolve an insoluble salt, but now it's got potassium hydroxide. Potassium's just along for the ride, a spectator ion, but hydroxide is in common with our insoluble salt. So I made a couple of ice tables on my Hinsky because they're so fun to make. So in water, it's kind of straightforward, what we talked about before, okay? You can let X be equal to the molar solubility in water. So it'll be what? X squared is equal to that 1.8 times 10 to the -11th. Okay, take the square root of that. That'll give you X. That's the molar solubility in water. And then for B, it looks like this. Okay, it's the same setup, but notice you are going to have an initial amount of magnesium ion, okay, from the water, which wasn't pure water. Okay. This one, you should be able to clearly use the simplifying assumption. The one that I kind of warned you about, that's later. So that quantity, 0.082 plus X, it's going to become what? 0.082. But make sure you state your simplifying assumption. So the simplifying assumption you need to state here for B would be if X is significantly smaller than 0.0862. Then quantity 0.0862 plus X is approximately equal to 0.0862. Okay, something like that. And then my hint for C actually is where I wrote all that stuff that needs to go away. So my hint for C, is down here. Ooh. Ugh. I just said C is similar to B. I don't know. But do you see where C is just right here? And in this case, you'll have an initial concentration of the hydroxide ion. So you need another ice table for C. On to, yeah, there it is. Okay. On to the next one. This one you don't have to do any ice tables. They're simply saying, what if instead of, B and C where you had magnesium, common ion, and hydroxide common ion, what if your insoluble salt is calcium carbonate and you have water that has sodium carbonate, water that has HCl, water that has sodium bisulfate, okay? What's that going to do to your the solubility of your insoluble salt, calcium carbonate? And I said, look for a common ion to reduce solubility. Anytime there's a common ion, it's going to reduce solubility. That's that one. No ice tables required. You can just do it visually. This one, not so much. So that's not the insoluble salt. That's saying basically instead of water, you have a 0.50 molar solution of sodium sulfate. And what does that mean? I kind of show it ionizing. That's not the equilibrium of interest. Okay. Now I went ahead and said there's a sludge at the bottom, so our solid of interest is silver sulfate. I just did that because that's how I think of it. Because it says the solution is saturated with silver sulfate. That's why I put the sludge. So if that's our sludge, if that's our precipitate of interest over here, now the problem doesn't say to do this that I have here in purple, but I did it. Why? Because it gets you down the road to understanding. The salt of interest is that insoluble silver sulfate, and you can kind of see how it ionizes, so you can see its KSP expression. Notice in the problem, I kind of showed you in orange, the other important thing about the problem is it gave you the molar concentration of the silver ion that's running around there in solution. Okay. So the question, haven't said what the question is. The question is, what is the value of KSP in this situation for silver sulfate using this information? So here's the deal. If you've kind of dissected it that far, do you see where basically you have the silver concentration to plug into your KSP expression from this orange number? That's your silver concentration. You have the sulfate concentration from your common ion. That was your sodium sulfate. Okay. So that's how that looks. This one took on a kind of a different look. And last but not least, it says again, instead of pure water, you're going to try to dissolve something that is in 0.0025 molar sodium sulfate. So I went ahead and kind of dissected what does that mean. Notice the solid of interest is calcium sulfate. Okay, so that's my sludge, calcium sulfate solid. Notice calcium sulfate, calcium sulfate is basically insoluble, but to a certain degree, it will ionize according to its KSP expression like that. So in this one, it says how many grams of calcium sulfate will be running around dissolved in the solution. So in other words, you have calcium sulfate running around because of this ionization, and they're asked, they say, what is the mass? What is the grams? That's your question. So I wrote some stepwise hints up here. I think this is how you have to do it. You have to knock out the molar solubility of calcium sulfate that has the common ion of sulfate in sodium sulfate. Get the new molar solubility. Once you have its molar solubility, use that 100 ml volume to get to moles of calcium sulfate that must be running around. Once you have moles, you can use the molar mass of calcium sulfate to get to grams. And so up there next to step number 1, I wrote in orange, that whole getting the molar solubility of calcium sulfate in something that has the common ion, in this case sulfate, that's actually what we did for the first 2 problems. That's the common ion. And this is the one that says, does the simplifying assumption hold? And I just go with it. I can remember in my notes, I think it doesn't, so you really need to use the quadratic, but I think we're fine. All right. And that's it. So let's do a few problems in the next part. Starting with the first slide, how's that? But we won't get to an assignment slide. It's looking like this unit's going to be kind of similar to what we've run into before, where we're going to get through the unit material a few days before you have your unit exam. I might try to have like some sort of like little quiz thingy again. I thought that was kind of fun. But did we like the survey okay? Survey works? Okay. So we'll see. All right. Precipitation reactions. One of the things that, when you teach chemistry, everybody's a little bit different, but one of the things I don't emphasize is, right up front, the different types of chemical reactions. I think there's a unit in your textbook that says, there's redox reactions, there's exchange reactions, but we did talk about exchange reactions before. They basically involve ionic compounds that if these 2 fingers are the cation and anion of one, cation and anion of another, at the other side they like switch partners. That is so cool. Okay. So it can be shown like this. And this in my office, I'm like, boy, the colors just kind of drive me nuts. but trying to show the switching partner. So an exchange reaction. It's for me. I say that at home, and it never is for me. And it wasn't until just this semester that I started thinking what bothers me about this kind of topic. And I think I know. So basically, if this is my beaker of water, okay, and if we take the example before with the, what was it, A, if we take AB plus CD, okay, so basically you end up with this kind of soup, okay, all in that water solution. Come on, catch up. Okay? Isn't that weird? Okay, it looks like this. Okay, so we have A cation, B anion, C cation, D anion, all running around there, right, in water. And we said they exchange, so the A goes with the D and the C goes with the B, right? That's the exchange part of it. But if a precipitate can form, you will get basically a sludge at the bottom, okay? So if either A, D, or C, B was a precipitate, you'd see it. Otherwise, to me, they just kind of are all chillaxing in that same solution together. Okay? It's not like they go automatically line up with each other. I guess my point is, if no precipitate forms, they're just one big happy family in there. But if a precipitate forms, you can identify the sludge at the bottom. There's what I mean to say. Okay, so here's an example, and let's kind of, you're going to want to be able to write these too. These are kind of fun. This is kind of like Gen Chem 1 sort of stuff, right? Okay, and hopefully, and we're covering this right now in intro. Okay, hopefully you can kind of see the cation and the anion, you know, exchanging partners. So the iron goes with the hydroxide, and the sodium goes with the chloride, right? You see it on the product side. But now you're going to have to remember everything we talked about in Gen Chem 1, where basically over here the formulas need to be neutral formulas. So where's an example? So for instance, can you see where this is iron 3? Do you see why this is iron 3? Okay, good. And so over here on the product side, when it forms the iron 3 hydroxide, we need 3 hydroxides, right? So actually that meant, if you want to look at it this way, that we needed 3 sodium hydroxide on the reactant side. So that you need to be able to balance them. But we're going to watch this video, and we've been talking a lot about, and that solid is pretty small there. We've been talking a lot about insoluble salts. Okay, so iron 3 hydroxide is insoluble. Okay, so actually when we work problems here on Friday, we're going to be focusing on that. Go ahead and write it, ionizing it into Fe3 plus and 3 OH minuses, and write the KSP expression. But in the meantime, let's look at this little video. Okay, so now I think I have 3 slides that basically, you can feel free to ooh and ah, but they're just still images. Across the bottom is the balanced exchange reaction, okay? And so, of course, these are both soluble salts. Over on the product side, be looking for the solid, okay? So let me go ahead, and I think here in a minute I have a slide that tells you this. But you need to be able to write the balanced exchange reaction and find the solid, and then for that solid, write the equilibrium. So in this case, it would look like this, right? PbCrO4. So lead 2 chromate, solid, in equilibrium with, I think I'll write them on the other side. Equilibrium with Pb plus 2 plus CrO4 2 minus chromate. While we're at it, let's go ahead and knock out the KSP expression. Now, these things don't take very long. Whether you use them or not, they just should kind of get you to thinking. plus 2 molar concentration of CrO4, 2 minus. Right? And quite frankly, it will get you partial credit. All right. So here, I don't know if you can see it, but we have a black precipitate. That's lead 2 sulfide. Lead 2 sulfide. So be able to write that equilibrium. It's all very doable. And I think this might be the last one. 2 soluble salts, iron 3 chloride, sodium hydroxide. On the product side, we have 1 insoluble salt. Hey, do you think you could ever like get 2 insoluble salts from your exchange reaction? Maybe. But anyway, the kind of the orangish stuff here is iron 3 hydroxide, and I think that's what you're using tomorrow too. One more. Silver nitrate and potassium chromate, both soluble salts, and they form potassium nitrate, which is also soluble, and silver chromate, which is insoluble. All right. So a minute ago when I picked on the, I can't remember which one I picked on, was it the lead 2 sulfide maybe? I picked on whatever that solid is over there. You need to be able to write the equilibrium for that solid with its cation and anion. Okay. Keep in mind that saturated solution represents dynamic equilibrium. Okay. That's how far I wanted to get. So we'll talk about KCs and all that Friday.